I'm Isaac. I just joined as director of AI at Taylor Geospatial. We are a nonprofit that essentially pushes forward geospatial projects from research to production. So we have identified that there's a huge gap in the geospatial industry where you have a lot of academics and people publishing, and then those kind of just like disappear into the black hole of publications and conferences. And then you have everyone else in industry that's actually like trying to make machine learning work and working with satellites directly, doing geospatial analytics, working with stakeholders and countries to like actually take that information of remote sense data and actually put it into actionable insights. And there's a huge gap in between there where a lot of people are making claims and papers and like producing really bad spaghetti code, and nobody wants to like spend time doing that. It's a little easier with agents now, but I think our main goal really is to work with professors and researchers and actually take what they've done and put it into production, whether that's in a like web app form. If we recently did a global scale inference of all agricultural field boundaries in the entire globe for the past 2 years, which has never been done before, surprisingly. And so doing more projects like that is basically what our goal is. I've also been working on a library called TorchGeo as a core maintainer for about 5-6 years now. And so really deep into like PyTorch, deep learning, geospatial coding, and open source software development. So if you have any questions about that, happy to answer that as well. So what is cloud native geospatial? And I think the first thing we have to talk about is like, what was the old way versus the new way? So the old way was you have some cloud storage, you have some NAS, some storage server, and you have some satellite imagery that NASA has loaded there, and you download 50 to 100 gigs to a terabyte of this data before you even start your analysis. And as you can probably imagine, some of you may not even have a terabyte, or even like 5 years ago have a terabyte of storage to download this data. And so you can quickly see like, if you only care about a small subset of the entire globe, you don't want to download the entire globe of data. You just want to download that subset. And so there's been a huge effort in the geospatial industry, mostly open source development, that's driven these new formats and schemas of types of data that we can convert the old way into the new way, stored in cloud storage, and allow you to only slice out a small subset. And this helps everyone essentially, because you can start streaming data fast. You obviously don't need a huge amount of compute to do all this. And I'll just kind of talk about that a little bit. So the cloud native stack, so these are the new formats. Before, satellite imagery or rasters would be stored as just TIFF file formats. And now we've produced this new thing called a cloud optimized GeoTIFF, which is basically a TIFF, but within that large image, each kind of like small area of the image is chunked, and you can directly request that for download only if you need it instead of the entire thing. GeoParquet is a similar structure, but for geometry. So you can imagine you go to OpenStreetMap or Google Maps and you see like building outlines. That's basically a polygon, which is a bunch of points that represent that building on the surface of the earth. And that's not a image, that's actually a geometry, a polygon, and those are stored in Parquet format. And so now we've produced this new thing called GeoParquet that just had the version 1 come out recently this year. And it's a similar structure where you have, let's say I have all the buildings, polygons in the world, and I only want to slice out a small subset. That allows you to do that. And then ZAR is the new hotness right now. It allows you to structure time series. So if I have a bunch of satellite images over time, you can store that as ZAR format because it's an n-dimensional array, but you can actually store like 3D time series as well. So it's basically as many dimensions as you want. And then PM tiles is essentially what I'll show you in some of my web apps that I'm going to display, but it very easily shows, like when you look at Google Maps and you're zooming in at different zoom levels, it's rendering that visualization on the fly. And that, you may not think about that, but that's actually a big deal on the engineering side to actually render that to not be super slow and be very snappy. And then cloud optimized point cloud, also similar to Cog in that if I have this large point cloud of the entire Earth, that's sensed from satellite data, we can actually slice out only a subset. And then the other issue there is that, okay, let's say I have terabytes of satellite imagery. How do I even know which of these files intersect like the area I care about? Like if I only care about Austin, Texas's bounding box, and I care about the past 24 hours, how do I search that? And so Stack is the big deal here, where it kind of sits on top of all of these and is this catalog and index that allows you to very quickly search all this data within a few lines of code. And so what you're going to see here in the next few slides in the few lines of code wasn't really doable like 4 or 5 years ago, you would have to like look at file names and try to interpret the date time from that and like what the intersection was. And you would have to do this for every single satellite because they're all different companies and organizations that run these, and they don't all have the same standard. And so really it's more about standardizing on sitting down and saying, hey, this sucks and we need to like do something about it. And so going on, this is kind of like the timeline of cloud native geospatial. 2015 was a big deal where all the Landsat satellite imagery finally made its way onto AWS. Instead of like local servers, you would have to like request the data being sent to you if you wanted it in bulk. The first stack sprint run by Radiant Earth, Stack 1.0, PM Tiles, Cloud Optimized Point Cloud, GeoParquet, ZAR V3 just came out with chunking and sharding, which is really cool. And it actually supports like geometries now. So there's GeoZar. And you can kind of see this is very recent. This is not like long term. And so we're kind of at the cusp of like all this fun stuff happening where you can do more with less compute. And so the cool thing though is that the data already exists. So we just like converted everything into a better format, but you can get petabytes of climate data from all the way back to like many, many years and decades. We have point clouds of the entire Earth over time. The Overture Maps Foundation, OpenStreetMap has a ton of geometry data available with tags. So you can get like this building and its height, and I'll show you here in a second. And then we are about to release like a global field boundary data set for 2024 and 2025 with over 119 million field boundaries across the globe. And that's all done by a machine learning model that we deployed. And so just real quick, this is how cogs actually work. It's a big image. We chunk it in a bunch of sub chunks, and you do a range request that says, I only want to get this little subset of it. And it automatically does that for you under the hood using HTTP range requests. That wasn't possible before. You'd have to download the whole thing. And then for zooming, for visualization, there's this concept of overviews where we actually resample. So we have the original image, we downsample it in half, we downsample that in half, and so on and so forth. So when you're running it into visualization or a web app, you can zoom in and it actually is like responding on the fly and serving those resized versions. And then similarly for GeoParquet, imagine I have 2.6 billion building geometries, and I only care about Austin. I can slice that subset out, and this allows you to do what's called predicate pushdown, which means I don't have to go and look at every single row to then find if it's a row that I care about, a geometry I care about. It's all in the metadata of the file. So I basically know each chunk and what the bounds that it covers. And so then I just go and grab the chunks that I care about very quickly. Because previously you would have to literally scan each row, and that's super inefficient. And then as I mentioned, Stack essentially lets you put in a bounding box and a date time and some other metadata that's stored. So like, let's say a lot of satellite imagery has a lot of cloudy scenes, and I want like the least cloudy in a month or the least cloudy in a year. You can do searches like that in a few lines of code using the PyStat client and some other, like Planetary Computer from Microsoft is a big one. Earth Search from Element 84, USGS has the Landsat look. And these are all catalogs that are run by these organizations, and they have APIs that are free, basically. So you can just immediately download data from that. And as you can see on the right, it basically, once you do the search, it gives you the assets that you care about. So you can then go feed that into other libraries that load the data. So this, if you want to query only the buildings in Austin, this is the code. That's it. You don't have to do any more. You pip install DuckDB. It's a Python library. You say, oh, I want to select what type of building, the height, the area, and geometry. I read from this S3 URL, which Overture Maps funds and keeps up. And then I say, I want everything within this bounds of Austin. And it immediately does this on the fly from your local computer, no cluster needed. And here's a visualization of this area. I can zoom in, and this is all this in your browser. And this kind of without needing like a ton of money or a ton of compute, like cloud compute. And then I'm doing the same thing here with ZAR. So I have the public Era 5 data. I'm requesting the 2-meter resolution temperature. And so I have a visualization here that's running. So you can see the 10-meter wind resolution. And this is all streaming on the fly every day or every hour of the past day. I'm not actually like doing any data download before. This is like live in the browser. And then if you want to search satellite data for UT Austin's campus, this is the query. I go to PyStat client, I open the Planetary Computer Stack API. I say, oh, I want this collection, Sentinel-2. I have this bounding box of Austin, and then I have this date range, and I say, oh, I want any image, the best image sorted by least cloud cover, less than 15%. I search these items, it's going to give me a Python dictionary, basically a bunch of apps, because these results will return like the full satellite image that intersects your AOI, and you need to still clip it. But essentially, this is what you get. So you get these RGB bands. If I plot them, this is 10-meter resolution of the campus of UT Austin right here. I've made a false color visualization where I've swapped out the blue band with the near infrared. And you'll see that if you do a lot of these analysis, near infrared band is very good for vegetation analysis. So you can see the red is highlighting essentially trees and other vegetation. And then NDVI is essentially the near infrared minus the red band normalized. So basically very, very bright green is essentially like healthy vegetation, and more brown is like built up for, but the National Agricultural Imagery Program. And every 2 years, they take from fixed wing aircraft, they fly the entire US. And so you have imagery from every 2 years of the entire continental US. And this is 1 meter, so 10 times the resolution. So you can see more details here, do more analyses, and this is the NDVI because Nate comes in RGB and near infrared as well. So I talked a lot about data, but like let's talk about AI and like what's out there, because we do a lot of machine learning on this data. So really everything is kind of trended from task specific models. While there are still task specific models, everyone is trying to follow the LLM route where we just pre-train LLMs, we just pre-train on a bunch of the internet, right? And we essentially get this good model that knows a lot about everything. And so we essentially have this trend going in research where you're trying to make geospatial foundation models that are basically generalists. I showed you like RGB, but there's climate data, there's radar data, and they all have their pros and cons. And so a lot of the effort into foundation models and geospatial is about being able to process all of these at the same time and produce either embeddings, which are like intermediate compressed versions of this data, or you take this model after it's been pre-trained and you then fine tune it on your task. And you typically will need less labeled data because it's already seen a lot of this data instead of starting from scratch. There's a lot of issues though. So no single model dominates. There's a lot of benchmarks out there right now. And everyone's proposing a new foundation model left and right. It's mostly driven by like organizations. IBM has a lot of foundation models. And so there's like Prithvi and some issues where some of the pre-training data that they use is only in certain areas. And really when you're building a geospatial ML model, you want it to generalize. So I want to be able to run it in the US, but also at work in Europe and in Brazil. And that's kind of a big issue is the spatial autocorrelation and not overfitting to like a specific area, unless you're planning to run it in the area, which is fine. But you kind of have to know in advance, like what you're trying to do with the model, like what is your goal? And then there's a lot of issues with like resolution. So a lot of the data comes in different resolutions. There's pros and cons with that. And then a lot of the climate data has been underserved. And then here's kind of the big one for me is a lot of benchmarks come out later that show that if you actually don't do any pre-training, you just train on your initial labeled data set, that still is a pretty good competitor for the pre-training, which kind of begs the question, do we even need to really pre-train on this? And so there's a lot of effort into trying to not just throw money at pre-training and trying to find out like, hey, can we like get more for less data? And then here's the big one too, most pre-training, as a lot of the data I already showed you is freely available online, but there's a large set of commercial companies, Black Sky, Planet, Maxar. They do have some open data that's available, but for the most part, a lot of these foundation models don't train on them. So they won't work for this data. And then just real quick, this is a little nerdy, but mass autoencoding, these are the two ways that pre-training happens typically. So typically in the past, it was contrastive learning, which is I have a single image and I augment it different ways. Maybe I change the brightness or I rotate it, and then I encode it through my model. I get this like nice vector representation of it. And basically, I want those vectors from the same image that have been augmented to be similar, and everything else to be dissimilar. And so that kind of pre-training without labels, other than the only thing you know about it is I have this image and I made two like random variants of it. That is actually a good pre-training loss function. And then mass autoencoding is very popular even in computer vision. And the idea is that transformer models, which LLMs use, they take in tokens, right? And the way that these transformer models essentially process images that are large is they then break them into small patches and then tokenize those. And you can exploit this process by dropping some of these tokens and saying, I've dropped some tokens from this image. From the ones that you have, reconstruct the ones I've dropped. And so this is actually a really good pre-training task, although there are some trade-offs, like it tends to like overfit to color like RGB bands instead of like some other of the other modalities. And so the other kind of axis is that there are foundation models that produce what are called patch embeddings versus pixel embeddings. So if I have a satellite image that's 256 by 256 pixels, a pixel embedding would be I have the same size and an embedding for each pixel. And a patch embedding would be from that single image, I get one embedding. And so the idea is that like the pixel embeddings, the patch embeddings are more efficient because you're taking that spatial extent and compressing it into a single vector. And the pixel embedding is saying, given the spatial extent, produce a bunch of pixel embeddings that are all somehow correlated with each other. And they all have their pros and cons. Obviously, like the patch embedding is more efficient because it's smaller. You're basically reducing the satellite image. Let's say I have 10-meter resolution and my patch size is 256. I'm reducing that by an order of 256, whereas the pixel embedding, you're just keeping the same size. And so they all have their pros and cons listed here. But the main thing here is the patch embeddings are nice for retrieval. And retrieval is kind of what I was talking about with contrastive learning, where I have a satellite image patch, and I let's say I care about this forest species patch of the Earth, and I want to find all other similar, like the most similar patches. That's essentially what retrieval is. And they do this the same way in LLMs, where I have this document, I ask this query, and then it does a scan in the embedded space of like what in that document is most similar to my request, and then it knows, oh, let me go then take that and put it into my context. So you imagine the Earth is just some really large document. And so I've talked a little bit about modeling, but I think the main thing that needs to be said here is that the modeling is the sexy part, but it's not the hard part. So 80% is always a pipeline. You will always, like when trying to deploy something, you will get stuck with like, oh, what post-processing do I use that gives me the best results? Now you have to try a bunch of stuff. It's never just like I train a model, I do inference, and then I like give it to a customer. It's like you have to put it back in a format that I talked about, the cloud native formats. You have to put it in cloud storage. You have to chunk it correctly, partition it correctly. You have to georeference it. You have to tile it so that it can be used for visualization with overviews. And then you have to sort of like, you have to monitor like what your like log the metadata, make a stat catalog for it. So there's a lot of other things that go on outside of just like train model and run it. And that's unfortunately like the hard part, but it's getting better with the cloud native tooling that's available. A lot of tooling is being rewritten in Rust when it's traditionally C++. GDAL is a really big library, but a lot of folks in the cloud native space are rewriting in Rust because you can use Arrow format, which is the Parquet format I was mentioning. And so that it's actually a really fun time because I also wrote a library that optimized this GDAL function in Rust with Claude, and it optimized it by up to 10x. So there's a lot of like performance that's left on the table because GDAL is such a core library and it won't accept like these very ambitious pull requests or changes to the library. So a lot of people are realizing that they can just rewrite it themselves and make an open source library, and they actually get used because people who care about performance will use it. And then GeoAI pipelines. So I mentioned TorchGeo. I don't talk about TorchGeo enough in this slide deck, but the meat and potatoes of TorchGeo is that the original library from PyTorch called TorchVision, which does computer vision with PyTorch, it kind of assumes you have these like, oh, I took an image with my phone and I have a label of cat or dog, right? Or I have a bounty box, that label of that. But it doesn't really handle these like large satellite scenes. And so really what TorchGeo does is instead of like, it kind of adopts this cloud native structure that instead of when you do training, you typically have some images, you have some labels, and then you have to sample patches from these large satellite scenes. And you have to do reprojection and resampling, all these kind of pre-processing to align this data together. And we essentially do this on the fly instead of you having to do it offline, duplicating your data. It just becomes very hectic. And so in this amount of lines of code, this is like how to train a model right here. I have some Sentinel-2 imagery in the data folder. I have some Viral Atlas label data in the labels folder. I decide, oh, I want the patch size to be 256 pixels, and I want it to sample 1,000 patches. I have some Torch data loader where I feed the data set in the sampler. And then I just iterate on that for batch and data loader. It will then load all and reproject and resample on the fly behind the scenes. So you don't have to, you can go about your machine learning. And that's really the core of TorchGeo, among some other things. And so this kind of is a similar structure. So at scale, you can imagine instead of sampling random patches, I want to sample like in a grid across this entire satellite scene. And this is essentially what the inference of TorchGeo does is you have this large satellite scene that you want to run a model on. You give it a grid geosampler instead of the random geosampler I showed you earlier. And then essentially you're going to have a bunch of patches, run the model on it, and then reconstruct this output prediction in like a COG or ZAR format. And you have to do this at scale because there's many, many scenes for the entire globe. They're all overlapping. And so this kind of like helps you structure how to do large scale inference. This is basically done on a distributed cluster. If you're going to do like the whole globe, you would want like a Kubernetes cluster or some AWS service that does this. But essentially, you can immediately see how it's like embarrassingly parallel, because if I have a bunch of satellite scenes, I just need to know, oh, how many patches do I have? And then I just kind of like chunk and distribute that out to as many workers as I'm willing to pay for. And so essentially, kind of diving into some lessons from fields of the world, we did all this. So we did patch extraction, distributed inference, overlap merging, where we actually did inference on overlaps, and then you do a weighted average so they look good. Because otherwise, if you do non-overlapping, you get these weird tile edge effects in the predictions, because it doesn't know like when a patch started and when it stopped. It typically does worse at the boundary of a patch. So that's a big one. Don't neglect that one, because people will roast you if you have tile effects. I do. So then you have to do a bunch of other post-processing morphology to kind of clean up the predictions. AI is not perfect. And so then from there, you're running on the entire globe, but maybe there's not fields. You're predicting there's fields in Alaska or in the ocean, and because you didn't train on that. So you need to do some kind of filtering from land cover. So you have some external land cover data set. You filter only on cropland so that you don't have to worry about like pre-processing and only running on certain satellite scenes. But then you're not done, because you have to polygonize that. I have a bunch of field predictions, but then I have to convert them to geometries. And there's a bunch of algorithms and knobs and figuring out how to do that become really tedious and hard. And so just what I'm trying to get across to you is that there's a ton of stuff that I just talked about without even talking about how to store that afterwards and serve it to a customer, or if you want to make it open source. But this is like what separates, the kids from the adults kind of situation, where if you want someone to use your product, you actually have to like go that extra mile. And it's not incredibly hard to like understand all these topics, but it's just extra work, and Claude is really good at it. And so here's actually the predictions. This is running live in the browser. You can go to slide 27. If we zoom in here, you can see it's like changing because we have different overviews. Yeah. So the colors are essentially the green. It just means the field boundary. But we also have this kind of structure of like how many fields are in that area. So at different zoom levels, as we're zooming in, it kind of lets you know like, hey, there's a lot of fields in this area if you want to zoom into it. And so here, they're still kind of loading in, but this is like a development server that we're going to launch on Earth Day that I'm just kind of sneak peeking it for y'all now. But the really cool thing is that we don't have this built in, but you'll be able to draw like a box and it'll download those geometries on the fly from that cloud storage. Essentially, it's meant for, and we run it on the entire globe. So it's meant for anybody, and it's freely available. There's no cost. We eat all the cost, and anybody who owns a farm who runs like a organization that, does field boundary analysis. The cool thing and the real next steps are like, what do you join this with? So there's a lot of like crop yields data. There's crop stress, crop health from these geometries, you can join it with that other data. And so we're not prescribing how people use that, but a lot of times different countries will have this data for their country, but not all countries will have this. And so the idea is that this movement is just kind of like give it to them and good things will happen essentially. And then you can also run inference on the fly. If you want to do like an older area, you can actually, let me zoom out here a bit. You can just click here. It's probably going to be a little slow because it kicks off a job. So it also kicks off a training run not a training run, inference run that takes in this AOI and will return you the field boundaries. But I'll let y'all play with that. For the sake of time, I'll just keep going. So the other cool thing I was talking about with geospatial foundation models is this idea of instead of like just fine tuning, what if I take the embeddings? And the embeddings are essentially like, once I do that pre-training and I chop off the head of it and I just take those intermediate outputs, those are learned features that are actually very useful, a useful representation that's smaller than the image. So I'm taking an image and I run it through the model and it compresses it into this list of values called vector. And this list of values in that embedded latent space, what they call it, is it makes things very similar, closer together. So if I take like the distance of those vectors or the dot products similarity, you can actually find pairs or like the top K similar results. And so what's really cool is, unfortunately, a lot of those have been like very large because they're using floating point 32-bit precision. So you can't really do this on the fly. You kind of do need a machine that can process the distance, especially if you're doing it at large scale. But one thing that my buddy and I from Microsoft AI for Good Lab, his name is Caleb, we've been playing around with the idea that like, what if we just like convert the floating point to binary? Like, what do you even need all the precision? And the fun fact is you don't. Surprisingly, a lot of the decisions in like how many values in this vector there are is it's not really like data driven. So it's just kind of like a predefined like value of like number of values. And so we actually find that a lot of these values are redundant. You could probably chop off like 75, 90% of them and you would still get good retrieval. And then furthermore, like you don't even need all the precision, all the decimal places. You can actually just convert it to like 8-bit integer, 4-bit integer, and then binary, where instead of like an actual float value, a decimal value, I have just ones and zeros. And there's a really fast algorithm called pop count, which processes the Hamming distance, which is like if I compare all the ones and zeros of each vector, this computes similarity. And so this allows you to actually run this in the browser to do this retrieval without a cluster. Everything is in cloud storage. And this is what I'm going to show you today in this Terabit app that I built. You essentially draw a region and it'll download those embeddings that intersect that region on the fly. And then you can then click some points you care about. So like, let's say I care about this field or type. I can click that. I can click a negative point, which is I want everything similar to this, but everything dissimilar to this. And so it'll compute the Hamming distance on the fly. So essentially it'll highlight what you're seeing here is it's highlighting the most similar values to like what your query is. And so there's a few visualization functions here, data set. And so these embeddings are done by the company called Legend, and they do basically embedding retrieval, but it's like paid and it's on a cluster. But they graciously like produce these global Sentinel-2 satellite image embeddings on S3 storage for free. And so essentially what all I've done is I've downloaded those, repartitioned those, uploaded them back to S3 storage. And so you can use this to find a bunch of interesting points. Let me just go right here. And it's all on the fly. So obviously, like if your network is not great, if your Wi-Fi speed is not great, it might take a little bit. Yeah, try it out, play around with it. It's a lot of fun. We're getting a lot of good feedback on this one. So yeah, let me keep going. Okay, so I want to talk about how I ship geospatial products today versus like a year ago. So everything you saw has just been created by Claude, like this entire presentation. All the apps that I showed you created by Claude. I just prompted it, and it's kind of blown me away. And my initial goal with this presentation was like, can I make something that's not a boring PowerPoint presentation? Make all these like videos, make all these web apps, and that's what my goal has been over the past like few months. Is like how far can I push like Claude to get me to 90%, and then I just take over the last 10%. And so that Terabit app I showed you, completely done with Claude. I'm not a front end developer. I like know my way around, but I'm not gonna like design anything. I just kind of know what looks cool. One of my prompts was make this look like Anthropic wrote it. And so this presentation, the slides, all done with JavaScript, run by a Markdown file. All the animations, the videos, I used 3 Blue, 1 Brown's Manim library. It's a Python library, and I just talked in my microphone and said, this is what I want to do for this slide. And it goes and creates the video. And then I just embed it in the slide. And then we've been drowning in the open source like world with a bunch of AI contributors. And so a lot of times what I do now to combat that is I use AI to like go through every day and look at all the open pull requests and summarize like what is easy for me to actually review and what's not, or I can have it give like an initial review. And then because basically Claude is talking to me, I have to manually review it, and then it just runs it back into Claude. So it's kind of easier if I just like cut myself out of the loop for a while, and then I jump in at the last mile. So what I kind of wanted to show is like domain expertise here is plus agents is like a force multiplier. It's made me incredibly more like this slide deck would have taken me probably a couple weeks on and off. Especially I have 2 girls now. I don't have a lot of time on the side. So being able to prompt Claude from my phone and review it has been really big. And I highly recommend all of you like think outside the box a little bit, not like completely depend on it for your work. You still kind of have to know like what a success criteria looks like what looks good. But definitely like use it for design and reviewing yourself. I've been doing a lot of research papers. And one thing I find is like, I've reviewed a lot that when I review now, I just feed it into Claude and I say like, what are the major issues in this paper? And then I start reading it. And surprisingly, like you'd be surprised how many people seem like they publish a paper, submit a paper and haven't even like had Codex review it. And it's kind of like the bar is up here now. Like you cannot not like just write it from scratch and assume it'll get accepted because everybody else is using AI now. So this is the blog that my buddy Caleb and I have been running. for a few weeks now. This entire website and blog is built with Claude and Markdown. It's mostly our ideas just because we've been in the space so long, but a lot of the the experiments, the compute is done in the web apps. It's done by us prompting. And so a lot of the writing, we have Claude and Codex kind of in tandem revising. But I think the thing to remember is like not all AI like written stuff is bad if like it comes from like a good idea. But definitely like review it after you're done. Like don't just like blind submit anything because that's a bad idea. Their hallucinations have been better, but it's still there. Trust me. It'll just like make up numbers. We run like a weekly, bi-weekly blog. Feel free to check it out. It has a lot of like really cool, like random ideas that we've had over the past few years in the GeoAI space that we just don't have time to like implement. But now with Claude, we can like just tell it to do it on the side for us. And then we kind of go and review like, was anything useful or not? And then what was cool, just cool ideas that we think would be interesting to share. The other thing I did was all the data I showed you for the planetary computer for the Stack catalog for downloading data. I made a few months ago a Stack MCP server in a VS Code extension. So now you can just, instead of saying like, oh, I have to go look up what collection, what satellite image data set I want to use, what climate data set, whatever, you just like tell your agent and it uses the MCP server to actually like figure that out for you and download the data for you. And it also plots it. The other annoying thing is like a lot of the data is in like raw sensor values. So it's not like a nice, pretty RGB 8-bit integer format. So you generally have to like convert it to some like nice plotted visualization. And I have a lot of tools already built in there for basically all the planetary computer data. And then if you're ever doing research, I found a lot of time that I simply like would repeat like, oh, I make a GitHub repo for a new idea. I want to add UV and all these like Python tools, and I want to add LaTeX templates. We write LaTeX code for papers and slides. And instead of like repeating that process, I just made a research repository that you can use as a template that has all the goodies in there that I use. And so like, for example, the slides.js folder is the same format as this slide deck that I'm showing you. So lots of good stuff in there. I basically write all my code, all my papers now, I write directly with the experiments. So all my experiments happen, and then I have it keep a update report in LaTeX, and then I have a GitHub integration to Overleaf, which is Overleaf, if you're familiar, is like shared Google Docs, but for research papers. So definitely check that out. It's free and public. And then I also made this one. So the USDA has their published version of crops called the Crop Sequence Boundaries dataset. And let me see if I can zoom out here. It's over all the US and it's in a really ugly format. And I just got really annoyed with it. So I had Claude download, convert it to GeoParquet, partition it, put it into S3 storage, and then make this front end visualization. And so you can see like each of the fields and their crop type, soybeans, whatever. And then you can see a little legend here of that. And then what's also cool is you can like turn them off, turn them on, satellite image off if you need to figure out where you're at. And then what's also cool is I can just like, oh, let's say I care about this field. I just hold shift and I draw a little box here and I click download AOI and it automatically downloads it for you. So that's kind of like the idea of the Fields of the World inference app that I was going to show you, but it's still kind of in development because we still have a couple weeks till we're going to announce it. So kind of wrapping up the bigger picture here. So I talked a lot about a lot of things, and maybe you might be confused about like what was your goal, Isaac? But the main idea here is that there's this flywheel that happens where people start working with models, start working with data sets, and realize, oh, this sucks. Like we need to like get together and figure something out to make things better. And then it goes back to people making schemas and standards, and then making more models, and then making global data sets, and kind of doing this loop of like iteratively like doing gradient descent to like find the optimal solution for all of us. And so if you're in any of these steps, like you're still producing value. And so I encourage you to like use AI coding agents to make web apps, to show this data, to get it into formats that don't suck and show people like how cool it is. I encourage you to like actually work on machine learning for these types of data sets. There's a lot out there. It doesn't have to be deep learning. A lot of people still use like basic random forest and linear regression and logistic regression, as long as it like produces a thing that is useful. It doesn't matter like how cool the model is or how trendy anything is. I think in the GeoAI space, the simplest things end up being the most useful, and trying to strip out any of that like for-profit, like marketing nonsense, like just give people some cool stuff and you're gonna get go viral for that. I think that's kind of like what I've seen over the past few years. And then what you can do today. So what I showed you was you can use PyStack client to search petabytes of data. Go do it. You can load this data with ODC Stack. Those are the 2 libraries you need. That's it right there. Then with GeoAI, build a retrieval system with embeddings, and then you can fine tune foundation models with TorchGeo. We have a bunch of foundation models, a bunch of training tools and trainers. If you just come with your data, it becomes a few lines of code. You can train a state-of-the-art model yourself. And so that's really cool. If you have any comments, we also have, I don't have a link for this, but we do have a TorchGeo Slack channel where actually it's become kind of like, it was originally just for TorchGeo, but now pretty much all the GeoAI researchers hang out in there. We post papers and tools and news, and you can talk to like the latest and greatest people in GeoAI just by joining that and like kind of hanging out and lurking. Feel free to lurk too. So yeah, that's all I had today. Here's my QR code for my website. It has all my socials on it: GitHub, Twitter, LinkedIn, all the good stuff. Email if you want to email me. Feel free to ask questions even after this or just advice. I'd love to review anything y'all are building.